We're going to talk about designing better batteries with Kandler Smith. So welcome.
Okay, so I've got a set of highly technical slides crammed into Pechacucha. I hadn't even heard of this format until 2 weeks ago, but we'll see what happens. So I'm from National Renewable Energy Lab. I'm a battery researcher. So who here has a battery in their pocket? I think we all do, yeah. So what I'm going to talk about is scaling up those batteries to something much larger scale, such as for the nice Tesla vehicles that you saw in Lauren's presentation, as well as for the grid. And so for the grid, in order for the grid to accept more and more renewable power, somehow you have to have a way to dampen out those fluctuating generation of solar and wind power. So what we are doing is working on computational models that help to accelerate the design cycle for batteries to help reduce the cost faster and improve the performance sooner. So a battery consists of a negative electrode, a positive electrode, and an electrolyte. It's this layered structure which then gets stacked up or wound up into a cylindrical structure, and then you gang together many of these in series and parallel, and you have a large-scale battery system. Cost of batteries is coming down dramatically. The worldwide production of lithium-ion batteries has doubled every year since 2010, so it's a dramatic cost reduction. And the magic point there that we're shooting for is 2022, a Department of Energy goal. If we can reach that number, that makes electric vehicles on par with conventional vehicles. So there's a steady stream of improvements which are coming along in the battery materials area. Expect that in the next 10 years or so, we should see a good 50% improvement in the energy density of batteries. It is a little bit difficult to see that some of these advanced materials are going to last as long as today's materials. What makes batteries so difficult is that if you talk to an electrochemist, they're at my left, your right side, or I guess that side, I should say, of this diagram, whereas electrical engineers or automotive engineers on this side. Computational models are an efficient way to let all these people talk to one another. So one of the main contributions that NREL, our group, has contributed is the scale up of electrochemical physics-based models to large-scale systems that consider temperature gradients and potential gradients throughout the systems. And that allows you to assess lifetime, assess safety of the batteries. And so one example here is this counter tab design has 2.5% imbalance during this particular drive cycle, whereas this other design has 12.7%. Companies like LG Chem today, because of these modeling results, have changed to counter tab designs, and so that's actually being implemented in vehicles. One of the computer-aided engineering of batteries programs is a Department of Energy program that I work on quite a bit. And one of the big things that we did starting in 2010 was to work with commercial software companies to implement these physics-based models into their platforms. So now these are in the hands of most automotive engineers as well as battery companies around the world. The electrochemical operating window kind of dictates where degradation mechanisms occur. Certain voltages trigger certain degradation mechanisms. One thing about lithium-ion batteries, even if you don't cycle them, they're degrading just due to calendar life limitations. And those are due to side reactions, and those are predominantly accelerated with high temperatures and high states of charge. So don't leave your laptop in your car, don't leave your cell phone in your car when it's really hot outside. Also, don't leave it at a high state of charge. If you can, don't charge it at night, charge it the next morning when you start to need it. That's counterintuitive to having usable energy in your battery, but that's what it is. So we've developed lifetime predictive models. One limitation of those today, they're not physics-based, they rely on experimental data. You need about 6 months at least of experimental data to make a lifetime projection. But the battery lifetime should last, depending on how you use it, anywhere from 7 to 20 years for some of the most advanced technologies today. So I would expect a Tesla with liquid cooling to last quite a long time. And we've been working with companies like Ford to understand how to develop systems around these batteries to last longer. A current project for us is delving to the lowest length scale, the microstructure, the complex geometry of the electrode. And at these lower length scales, what we do is start out with CT imaging, so just like in your doctor's office, but at a much smaller scan than your knee or whatever it is that you're in your doctor's office for. From there, we can directly simulate the physics on top of this and see how that impacts the battery's uniformity of utilizing all the active materials that go into there. Safety is still kind of an issue. Lithium-ion batteries are flammable. There are solid electrolyte materials that are coming along which should drastically improve the safety of batteries, but there's a lot of engineering design that goes into ensuring that if a single cell has a little small internal defect or is crushed externally, won't go into a catastrophic failure and propagate to the neighboring cells. So we work with Sandia National Labs. We have models of internal short circuits, thermal runaway. These models match up pretty well and can predict cell-to-cell propagation, also the instigation of the thermal runaway. Today's batteries in electric vehicles, the vehicles are conservatively designed, adding extra skeletal structure on the vehicle to prevent the batteries from getting crushed. However, the batteries can they can take some deformation and still last. So we're looking to reduce the weight of these vehicles by understanding exactly what the batteries can tolerate. In order to do that, we start with component scale measurements at single cell levels, scale these up. We're even working with the US Army on bullet penetration simulations, which is something that, how to validate that, I don't exactly know. I'll let you guys read this quote. You can talk to me later on about what my credibility level is here. But hopefully we're reducing the black magic that goes into the batteries. It's been a long time since, lots of different researchers need to work together in order to make these batteries work. Thank you.